Okay, so now for this last part, we're going to talk about some remarkable endomorphism in a vector space, and that could be finite dimensional most of the times. But also it could be non-finite dimensions, but we're going to see. Okay, so basically we have three important items. One is very easy. It's just what's called the homothetic transformation, and actually it just looks like a scaling. It is something that if you're in finite dimensional spaces, you can represent it by the matrix identity times scale lambda, a scalar value lambda, or you can write it that it's written as scalar value lambda times the identity of your domain. Okay, so that's one thing, and it's very trivial to find out. Next thing is going to be the projection. All right, so what about the projection? So it's really something that, we need two things in order to do a projection. We need um, somewhere to project onto, and we need a direction to project along. Okay, and so how does that work? So let's assume we're in a vector space called E, and E can be written as the direct sum of two subspaces. Okay, so we've got two examples here. Here in 2 dimensions, I have one direction here and another direction here, and so those two directions, they make the plane R2. Okay, so I can write that R2 is given by the sum of the vector space obtained from this direction and the vector space obtained from this direction. Okay, and another example, which is about the best thing we can draw here, is that kind of stuff in R3. In R3, you can assume that you've got one plane, so one plane with so two directions, and a third direction, so maybe more precisely this one. Or here I drew it like an orthogonal frame, but it doesn't have to be an orthogonal frame. You know, I need just three vectors in order to make three directions in order to span the whole of R3. So maybe I could take a third direction which wouldn't be so orthogonal to this plane. Okay, that's going to be more general. All right, so what are we going to do? So let's take this example in R3. Assume that you've got some point M in R3. You know that if I'm considering this vector, there are those two vectors that are spanning the plane plus this vector that is spanning this direction, which is not on the plane, I can express M as in this basis, and more precisely, it's going to have one component here and one component here. I can take one component that belongs to that space. Okay, so let's call that x1, and that component which would belong to this line, which would be x2, and so that my point x can be written as x1, which is going to be itself the sum as let's give those some names: e1, e2, e3. Okay, x1 would be x11 e1 plus x12 e2. Okay, plus another component x2 that would be on the third direction. Okay, plus x2 times, according to my notations, which would be x2 times e3, and that whole thing is giving you the components of x in basis e1, e2, e3, which doesn't have to be the standard basis of R3. All right, so the thing is that I can really see this as having two parts. One part which belongs to, let's call that, what are the notations that I used? F and G. So let's say that R3 is my whole space E, and that will be F, my plane, and G, that direction. So I've got one part here that belongs to F, okay? This part here, and another part here that belongs to G, this one, all right? And what I can say is that x1, this one, is the projection onto F along the direction G of my point M with which would be X. Okay, so that's the projection, right? So let's sum it. If you can describe your space as the direct sum of two subspaces F and G, that means that's the definition of a direct sum. It means that there exists a unique pair x1 and x2 that belong to x1 belongs to F, x2 belongs to G, such that you can decompose x as the sum of x1 plus x2. And so we can describe the projection of a linear map the projection as of on F along G is a linear map such that we decide to keep only the first part, the part that belongs to F. Okay, so you have all X can be written as having two pieces, one piece in one first subspace, one second piece in a second subspace, and those two subspaces, and this decomposition is unique, so that these two subspaces make a direct sum. Okay, and so the projection on F is just to say, well, I'm just going to keep that first piece here, okay, along the direction G. It's just that the complement that we are keeping is the x2 that belongs to G, okay? And so if you describe this in terms of linear maps, so that's a linear map that we're calling P. So P is the stuff such that for any x we associate the x1 part, okay? So what do we have? How can we characterize this map P? It's such that the space F is going to correspond to the image, right? To the image of my projection, and anything that would belong only to the second space, well, it has no component in the x1 space, so that belongs to the kernel, right? Okay, so anything that belongs to that direction G has is projected as 0 on the plane, right? So that belongs to the kernel of my map, right? And so you indeed have that in that case, E is the sum of the image plus the kernel, right? One way to characterize a projection, and we're going to see the proof of that, is to say that, well, I've got a projection if and only if I compose twice my map with itself. Well, if I compose my map with itself, it's just as saying, well, it's just exactly the same as doing it just once, okay? So why is that? Because if I take some x in E, I use my projection, I keep the x1 element, and that x1 element, well, it belongs to my space F here. It belongs to my space F, this one, all right? So, and if I use P again, well, I'm just going to stay where I am, right? I started from my point M, projected it onto the plane, it gave me that component, and now I'm here. If I project it again, I'm going to stay there, I'm not going to go anywhere else, all right? That's what projections do, right? So that one way to characterize this projection is to say that if I've got a map such that if I compose twice my map, well, if I compose my map with itself and it just has exactly the same effect as just doing it once, then it is a projection, and vice versa. Okay, here you've got another illustration. So it was in 2 dimensions. So you have one first dimension, this direction here, one second direction here, and you see for any x, you've got this projection onto the blue dimension along the direction k, which will give you this value here, If you take one item here, it's going to be projected as this item. If you take this item, it's going to be projected as this one, okay? So that these are things you can visualize. So you can visualize this in R2. You can visualize this one in R3, okay? You can also imagine the contrary, projecting onto a line by using the direction of a plane. Well, it's just, for instance, here, the projection of my point M onto subspace G would be that x2 component if I take it in the direction of the other one. Okay, so maybe we can go to the proof of this. Okay, so let's prove that P is my projection onto image of P along the kernel of P, okay, onto F in the direction along G, if and only if P compares with itself is itself. Okay, so let's prove that. Let's, as usual, we have two sides to the equivalence. So first thing, direct implication. If X, so we already saw that if X belongs to E, P applied to P of X is going to be P of X1. I'm using the fact that any X can be decomposed as X1 plus X2, where X1 belongs to F and X2 belongs to G. And F corresponds to the image of P and G to the kernel of P. Okay, so P of X corresponds to P of X1, and as if we assume it's a projection, we know that X1 already belongs to F, so that's going to be X1. All right, so we indeed have that, which is P of X. That's P compares with itself is equal to P alone. All right. Second part of the proof, the indirect implication. So let's assume we have that P composed with P with itself is equal to P, and we want to show, do we have that E is equal to the major of P plus the kernel of P. Okay, this is what we want to prove. All right, so what we can do is we can write X as being, it's quite a simple trick, but it's often very useful, as P of X plus X minus P of X. And that's a very important characterization that we can use for projections. So obviously this part belongs to the image of P, because well, it's P applied to X. And what we want to prove is, does that belong to the kernel of P? Okay, so let's apply to P to X minus P of X and see if we get 0. So that's going to be P of X, I'm using linearity, minus P applied to P of X. Okay, but as we assumed that P applied to P, minus P compares with P was actually P of X, we indeed get that it is 0. So we have that it does belong to the kernel of F. Okay, so to the kernel of P, sorry. So that's fine. Now we need to prove that we have a direct sum. So we want to look at the intersection of the image of P and the kernel of P. Is it equal to the 0 of E? Okay. So if X belongs to that intersection, in particular, it belongs to the kernel of P, so P of X is equal to 0. Right. If X belongs to the image of P, it means that there exists Y such that P of Y is equal to X. Right. But using the hypothesis that P composed with itself is P, we get P composed with P of Y is equal to P of Y because of this assumption, but it's also equal because of the previous line to P of X, right? So that I get that P of Y is itself equal to X by assumption, by this assumption, and also that P of X is equal to 0. Okay, so x is equal to 0, so that the intersection is only 0, and we have a direct sum.